In this video, we are going to be looking at the arithmetics of limits to see how convergent sequences behave when we add them, multiply them, divide one by another, or if we just compare convergent sequences. So let me start with the first theorem, which says that if an and bn are convergent sequences, with limits a and b respectively. So what I mean by that is an converges to a and bn converges to b as n tends to infinity. So if that happens, we have two convergent sequences, then the following statements are true. First, the limit of the sequence that is obtained by adding the nth term of each of these sequences. So adding these two sequences forms a new sequence, and that has the limit that is the sum of the limits of the sequences that we started with. Second, the limit of the sequence that we obtain by multiplying terms in these two sequences will have the limit that's the multiple, that's the product of the limits. And finally, the limit of the sequence that we get by taking the ratio of the terms of these two sequences will have the limit, this sequence will have the limit that is the ratio of the limits of the original sequences. In this last statement, I should add that we shall not divide by 0, so terms in bn shouldn't be 0, and also the limit itself, b, should not be equal to 0. Okay, let's prove at least the first of these. All three statements can be proven in a similar way. Let's go for the first one, and let me show how you prove that. So what we know is that both an and bn are convergent with limits a and b respectively. So we want to have a look at the distance of this general term in this sum of sequences from a plus b. Okay, so what we'll do is, since we have convergence for an and bn, we have for all epsilon greater than 0, there are indices n1 and n2 such that, maybe I should call them NA and NB, such that AN is closer to A than epsilon for all indices greater than NA, and similarly BN is closer to B than any previously fixed epsilon for all indices greater than capital NB. Okay, so what we can do now is to look at the difference, the distance of AN plus BN and A plus B, and what we can do here is to group the terms in a different way, so that we have AN minus A plus BN minus B as our two terms in the absolute value. And now we can apply the triangle inequality, which will give us something that is greater than or equal to the previous expression, and it will be the absolute value of an minus a plus the absolute value of bn minus b. Okay? But both of these terms can be given the upper bound of epsilon if we have chosen little n to be both bigger than n capital N B, capital N A and capital N B. So if that happens, then we can say that this sum is less than epsilon plus epsilon. So it's less than 2 epsilon, and this happens if we have little n greater than both capital NA and capital NB. So the way to write is that it's bigger than the maximum of these two numbers. Okay? So basically what we have seen is for all positive epsilon, we can find an index such that for indices that come after that, and the terms in that sequence, which is the sum of two sequences, get closer to the sum of the limits than 2 epsilon. But of course, we could relabel everything to have the proper definition of convergence. So whether it's 2 epsilon or epsilon doesn't make a difference. It still means that the limit of an plus bn is a plus b. So this concludes the proof. As I said, the rest of the theorem can be proven similarly. Now, with using these handy rules, we can calculate lots of limits if we know only a few types of limits. All sorts of combinations of these can be now calculated. So what I would like you to do is to consider the following example: the limit of the sequence n cubed minus 2n squared plus 1 divided by 3n cubed plus 4. So what I want you to do is to pause the video and think about how you can apply this theorem to calculate the limit. Okay, I hope you paused it, and I hope you were able to calculate the limit. So the way to do it is to realize that the n cubed term, both in the numerator and in the denominator, are the dominant terms. They are the ones growing the fastest. So if you just simply bring it up out front and make it so that it remains equal, these two expressions, you will have, of course, 1 minus 2 over n plus 1 over n cubed in the numerator, and in the denominator you will have 3 plus 4 over n cubed. Okay? Of course, we can simplify with this n cubed, so that is basically what we've been doing here. And what we are left with is now an expression where each of these terms, all terms, go to 0 except for the very first one in the numerator and the denominator. So both, well, all of these 2 over n, 1 over n cubed and 4 over n cubed, they all have the limit 0. So applying these formulas means that we can take the limits of each of these terms and get the answer 1 minus 0 plus 0 divided by 3 plus 0. So in short, 1/3 is the answer. Okay, I hope you got it right. For the next statement, we will consider the proposition, which is often termed as the comparison of limits. So we will be or limit comparison. Which means that if you have two sequences which can be related to one another in some way, so let an and bn satisfy the following inequality. Let's say that an is greater than or equal to Bn for all indices n. Okay, so An is always greater than or equal to Bn. Now then the following statements are true, assuming that they are both convergent and An converges to A, to the limit A. This is another way of writing that the limit of n is A, as n tends to infinity, and the limit of Bn is, the sequence Bn is B, as n tends to infinity. So assuming that they are convergent, we have the same inequality for the limits. So taking the limit of two convergent sequences that are in some relation will respect that relation. The limits will have the same inequality. Okay, and the second part of this statement is that if we now assume that the smaller sequence that has less than or equal to terms diverges to plus infinity, that will push the sequence with the greater terms also to plus infinity. So assuming that the smaller sequence Bn diverges to plus infinity as n tends to infinity, we have An also diverging to plus infinity as n tends to infinity. Okay, so these are the two statements. Let me prove at least one of them. So this is very useful when comparing two sequences and finding that that they are converging to have the same relation for their limits, and if one of them diverges to plus infinity, the smaller one, it will push the larger one with itself to plus infinity. So let's see the first one. Let's prove it indirectly. Let's assume that instead of having the same relation for the limits, by some miracle, A would be less than B. Then take epsilon to be half the distance between B and A. Now B is assumed to be the greater number, so B minus A is positive. So we take half that positive number and find n such that An is closer to A than epsilon and Bn is closer to B than epsilon, for this epsilon, for all little n that come after capital N. This certainly can be done because these are assumed to be convergent sequences. So by definition, for any previously fixed positive number, we can find such an index. Okay, so what we'll do now is we can take epsilon, which was our B minus A divided by 2. We can write this as with an absolute value being B minus A halved in absolute value. But then we can do the trick, which is introducing An and Bn into this in a tricky way. So what we'll do is we'll introduce both An and Bn into this in a tricky way. So what we'll do is we'll say, okay, let's have An minus A. Then, of course, we want to have a minus an, but let me add first bn, then subtract an. So now I got rid of the extra term of an. Then, as a last step, have, of course, b should be there, and minus bn. So I have to subtract bn at a certain point. So if I write b minus a in this tricky way and group these terms in such a way, what I see immediately is that bn minus an in the middle is certainly making it's certainly making this number smaller. Okay, so what I can do is I can right away get a number that is greater than or equal to this previous number if I just forget about the middle term and get an minus a plus b minus bn in absolute value halved, and then I can apply now these inequalities. These inequalities, if I use the triangle inequality first, I can get half a number that is greater than or equal to the previous one, and looks as follows. It's half the absolute value of an minus a plus the absolute value of bn minus b, which is the same thing as the absolute value of b minus bn. Okay, so now we can make the strict inequality, that this is we get a strictly greater number if we have, instead of these absolute values, epsilon in both cases. But it is halved, so epsilon plus epsilon divided by 2 is epsilon. And again, we have arrived at a contradiction, getting that epsilon is a number that is less than itself. So that's a clear contradiction, indicating that our initial assumption that the limits had a different relation than the sequences was false. Okay, so for the second point, we can prove it in a more straightforward way, because if bn diverges to plus infinity, then for any number we can find an index after which bn will be greater than that fixed previously fixed number. But then of course an, because of this relation, will be also greater than that previously fixed number. So it is more straightforward than the first statement. Okay, so that can be also easily proven. Finally, so to have a final theorem, which is very important, is the so-called sandwich rule or squeeze rule. So this is called the sandwich rule, or squeeze rule. Is also a name that is used about this next theorem, which states that if an and cn are two sequences which have the same limit, the limit L, so they have the same limit L, and an and cn sandwich a third sequence bn for all indices n, then bn also converges to that limit L. Okay, so to prove this, we just simply have to notice that in order for an to converge to L and cn to converge to L, we have to use the definition of convergence. So this will be just a very sketchy proof, but basically for all epsilon greater than 0, there is a number such that an will be greater than or equal to L minus epsilon and less than or equal to L plus epsilon, but that will be also true for Cn, and Bn is sandwiched in between these two sequences. So as I said, Cn should be less than or equal to L plus epsilon. But the way we have written these inequalities, because we have this sandwiching property, is that just the same thing for Bn, that we have the definition of convergence to the number, the limit L. Okay, so this is just happens for all n that are indices n that are greater than capital N. So Bn by definition is then convergent. By the definition of convergence, it converges to L. Okay, I hope you have enjoyed this video, and I'll see you in the next one.